To calculate the current draw of a coil, we can use Ohm's law, which states that current equals voltage divided by resistance. In this instance, we have a 120 volts coil with a resistance of 2.0 ohms. Therefore, the current I is equal to 120 volts divided by 2.0 ohms. The result of this calculation is 60 amps. The coil will draw 60 amps of current. The high current draw is due to the low resistance of the coil. Resistance is a measure of the opposition to the flow of electric current. A low resistance means that the current can flow more easily. In the case of a starter coil, the low resistance is necessary to create a strong magnetic field when the coil is energized. This magnetic field is used to engage the starter gear with the engine's flywheel, starting the engine. Several additional considerations are worth mentioning. Firstly, the current draw can vary slightly depending on the specific design of the starter and coil. Secondly, the coil's resistance may change slightly over time due to factors such as temperature and wear. Thirdly, it is important to use the correct starter coil for the specific application to ensure proper starting performance and avoid damage to the starter. Let's elaborate further on Ohm's law and how it applies to electrical circuits. Ohm's law is a fundamental principle that describes the relationship between voltage, current, and resistance in an electrical circuit. It is expressed as voltage equals current times resistance, or voltage equals I times R. Rearranging the formula, we can also state that current equals voltage divided by resistance, or I equals voltage divided by R, and resistance equals voltage divided by current, or R equals voltage divided by I. Voltage measured in volts is the electrical potential difference between 2 points in a circuit. It is the driving force that pushes electrons through the circuit. Current, measured in amps, is the rate of flow of electric charge. It represents the number of electrons passing a given point in the circuit per unit of time. Resistance, measured in ohms, is the opposition to the flow of electric current. It impedes the movement of electrons through the circuit. In the context of a starter coil, the coil acts as a resistor in the circuit. When voltage is applied to the coil, current flows through it. The amount of current that flows depends on the resistance of the coil. A low resistance coil allows more current to flow, while a high resistance coil restricts the current flow. The starter coil's low resistance is crucial for generating a strong magnetic field. The strength of the magnetic field is directly proportional to the current flowing through the coil. A higher current produces a stronger magnetic field. This strong magnetic field is necessary to engage the starter gear with the engine's flywheel. The magnetic field pulls a plunger or armature, which in turn moves the starter gear into position to mesh with the flywheel. Once the starter gear is engaged, the starter motor can crank the engine, initiating the combustion process. It is important to note that the current draw of the starter coil is typically very high, especially during the initial starting phase. This is because the starter motor needs to overcome the inertia of the engine and provide enough torque to start it rotating. The high current draw places a significant load on the vehicle's battery. That is why a healthy battery is essential for reliable starting. Over time, the resistance of the starter coil can change due to factors such as temperature and wear. High temperatures can increase the resistance of the coil, while corrosion or damage to the coil windings can also alter its resistance. Changes in resistance can affect the current draw and the performance of the starter. If the resistance increases, the current draw will decrease, potentially weakening the magnetic field and making it harder to start the engine. If the resistance decreases significantly, the current draw may become excessive, potentially overheating the coil and damaging the starter. Therefore, it is important to periodically inspect the starter coil for signs of wear or damage. If the coil appears to be corroded, damaged, or has significantly different resistance than specified, it should be replaced. When replacing a starter coil, it is crucial to use the correct part for the specific vehicle and engine. Different starters have different coil designs and specifications. Using the wrong coil can result in post-starting performance damage to the starter, or even damage to the vehicle's electrical system. The manufacturer's specifications should be consulted to determine the correct starter coil for a particular application. In addition to the starter coil, other factors can also affect the starting performance of an engine. These factors include the condition of the battery, the starter motor, the wiring connections, and the engine itself. A weak battery may not be able to provide enough current to the starter, resulting in a slow or failed start. A faulty starter motor may not be able to generate enough torque to crank the engine. Corroded or loose wiring connections can restrict the flow of current to the starter. Engine problems, such as low compression or incorrect timing, can also make it difficult to start the engine. Therefore, a comprehensive diagnosis should be performed to identify the root cause of starting problems. This may involve testing the battery, the starter motor, the wiring connections, and the engine itself. By systematically checking each component, it is possible to pinpoint the source of the problem and implement the appropriate repair. Understanding Ohm's law and its application to electrical circuits is essential for diagnosing and troubleshooting electrical problems. By using Ohm's law to calculate current, voltage, and resistance, it is possible to identify faulty components and ensure the proper operation of electrical systems. In the case of a starter coil, understanding the relationship between resistance, current, and magnetic field strength is crucial for ensuring reliable starting performance. Remember that the formula I equals voltage divided by R is a cornerstone of electrical calculations. Understanding how to use it will allow you to solve a wide variety of problems. To recap, a 120 volts coil with 2.0 ohms resistance will draw 60 amps of current. This high current is needed to create a strong magnetic field to start the engine. Always ensure the correct coil is used for the application and be aware of factors affecting resistance. Let's consider a few examples to further illustrate the application of Ohm's law to different scenarios. Firstly, imagine you have a 12-volt car headlight with a resistance of 4.0 ohms. Using Ohm's law, the current drawn by the headlight is equal to 12 volts divided by 4.0 ohms, which equals 3 amps. Secondly, suppose you have a 240 volts appliance with a current draw of 10 amps. The resistance of the appliance is equal to 240 volts divided by 10 amps, which equals 24 ohms. Thirdly, if you have a circuit with a resistance of 100 ohms and a current of 0.5 amps, the voltage across the resistor is equal to 0.5 amps times 100 ohms, which equals 50 volts. These examples demonstrate how Ohm's law can be used to calculate current, voltage, or resistance in various electrical circuits. By knowing any two of these values, you can easily determine the third value using the appropriate formula. In addition to Ohm's law, there are other important concepts to understand when working with electrical circuits. One such concept is power, which is the rate at which electrical energy is consumed or produced. Power is measured in watts, and it can be calculated using the formula power equals voltage times current, or power equals voltage times I. Another important concept is series and parallel circuits. In a series circuit, components are connected end to end, so that the same current flows through each component. The total resistance of a series circuit is equal to the sum of the individual resistances. In a parallel circuit, components are connected side by side so that the voltage across each component is the same. The total resistance of a parallel circuit is less than the smallest individual resistance. Understanding these concepts, along with Ohm's law, will provide a solid foundation for understanding and working with electrical circuits. Let's consider some safety precautions when working with electricity. Firstly, always disconnect the power supply before working on any electrical circuit. Secondly, use insulated tools to prevent electric shock. Thirdly, never work on electrical circuits in wet or damp conditions. Fourthly, wear appropriate personal protective equipment such as safety glasses and gloves. Fifthly, be aware of the potential hazards of electricity and take precautions to avoid injury. By following these safety precautions, you can minimize the risk of electric shock and ensure a safe working environment. In summary, understanding Ohm's law, power, series and parallel circuits, and safety precautions is essential for anyone working with electrical circuits. By mastering these concepts, you can diagnose and troubleshoot electrical problems, design and build electrical circuits, and work safely with electricity. Remember to always consult the manufacturer's specifications and follow industry best practices when working with electrical equipment. With proper knowledge and precautions, you can safely and effectively work with electricity. Let's also talk about the impact of temperature on resistance. Generally, the resistance of most conductors increases with temperature. This is because as the temperature rises, the atoms in the conductor vibrate more vigorously, making it more difficult for electrons to flow through the material. This increased opposition to electron flow results in a higher resistance. The amount by which the resistance changes with temperature is known as the temperature coefficient of resistance. Different materials have different temperature coefficients of resistance. Some materials, such as copper and aluminum, have relatively low temperature coefficients, while others, such as tungsten, have relatively high temperature coefficients. The temperature coefficient of resistance is an important factor to consider when designing electrical circuits that will operate over a wide range of temperatures. For example, if a circuit is designed to operate at a high temperature, the resistance of the conductors will increase, which can affect the performance of the circuit. In some cases, it may be necessary to use special materials with low temperature coefficients of resistance to minimize the effects of temperature on the circuit. In addition to conductors, the resistance of insulators can also be affected by temperature. However, in the case of insulators, the resistance typically decreases with increasing temperature. This is because at higher temperatures, more electrons in the insulator can gain enough energy to break free from their atoms and become mobile charge carriers. This increased number of charge carriers results in a lower resistance. The temperature dependence of resistance is an important consideration in many electrical applications. For example, in temperature sensors, the resistance of a material is used to measure temperature. By carefully selecting a material with a known temperature coefficient of resistance, it is possible to create a highly accurate temperature sensor. Let's now briefly touch on the National Electrical Code, NEC. The NEC is a set of standards and guidelines for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is important for electricians and other electrical professionals to be familiar with the NEC to ensure that electrical installations are safe and compliant with regulations. The NEC contains numerous tables that provide information on the allowable ampacities of conductors, the sizing of overcurrent protection devices, and other important electrical parameters. For example, NEC Table 310.15b16 provides the allowable ampacities of insulated conductors rated up to 600 volts, based on their insulation type and ambient temperature. These tables are essential for ensuring that electrical installations are properly sized and protected. The NEC also contains requirements for grounding and bonding electrical systems. Grounding is the process of connecting electrical equipment to the earth, which provides a low impedance path for fault current to flow back to the source. Bonding is the process of connecting different metal parts of an electrical system together to create a continuous electrical path. Grounding and bonding are essential for preventing electric shock and minimizing the risk of fire.